Welcome to Maths with EJD. We're still talking about differential equations, and in this video, I'll be focusing on higher order linear differential equations. Previously, we had considered first order, second order, and order. So, this video takes care of any other, maybe third, fourth, fifth, sixth, seventh, and all the rest. Um, so that's what we have here. Okay, talking about higher order differential equations. Let's have an overview. Okay, so a higher order linear differential equation involves derivatives of an unknown function up to order n. And when we solve the differential equation, we are looking for that unknown function. So the general form is the nth derivative of the function plus Pn minus 1 of x, y raised by n minus 1, all that, all the way down to P1 of x, y prime, plus P naught of x, y, and that is equal to Q of x. So this is a more general form of all the forms we've been seeing all along. Okay. So where yn is the nth derivative of y of x that we are looking for. Then all the PIs, all the Pn minus 1, Pn minus 2, and all the rest of them. So all the Pi of x's are functions of x. They are functions of x, and they are possibly constant. In the case of they are possibly constant, right? They are possibly constant. Okay. Then of course Q of x is that thing we know. Q of x is the non-homogeneous term. Is the non-homogeneous term. Okay. So if Q of x is equal to 0, if Q of x is equal to 0, the equation is homogeneous. Okay. So let's go ahead and talk about how to solve. So when we're looking at different techniques before now, especially for non-homogeneous equations, the last thing we considered was variation of parameters, and we discovered that if the situation is more complicated, then that may be what we resort to. Okay, so solving techniques for higher order equations. Okay, so for equations of the form yn plus an minus 1, y raised power n minus 1, plus all that, plus a1 y prime. That's just like what we saw up there. Then a naught y equals 0. Of course, this is clearly homogeneous because it is equal to 0. So for equation of this form, where ai are constants, the solution follows these steps. Uh, Number one, you find the characteristic equation, find the characteristic equation by substituting, I think I just demonstrated this in the previous video, by substituting y equals e raised to power rx, leading to r raised to power n plus an minus 1, r raised to power n minus 1 plus all that up to a1r plus a naught equals 0. And this is the characteristic equation. Okay, so that's step one. So step two now, you now solve for, so you solve for r, which are the roots. They are the roots of the characteristic equation. They are the roots of the characteristic equation. Okay. Then, so we now have all the conditions now. Uh, so we say that distinct roots, distinct, distinct roots, distinct real roots, R1, distinct real roots, R1, R2, up to Rn, give solutions of the form yc equals c1 e raised by r1x plus c2 e raised by r2x plus all that plus cn e raised by rnx. Okay, those are for distinct roots. That's the first situation. Then we also have possibilities of repeated roots. So if you have the same roots repeated all over, so repeated roots, R1 equals R2 equals all that up to Rn, that all the roots are the same, would actually give YC. I mean, if you can, yeah, you can call it YC. That's complementary solution. YC will now be C1 plus C2x plus all that K plus everything down to Cm x raised by n minus 1 e raised by r1x, because the roots are the same all the way. That's when you have repeated roots. And then we can also talk about complex roots. Complex roots, complex roots would give complex roots like r say r now is equal to alpha plus beta I, or I beta if you like, will give y of c, will give yc equals e raised by alpha x into c1 cos beta x plus c2 sine beta x. We saw this much when we're talking about the characteristic equation method for non-homogeneous equations. So that's for homogeneous equations rather. So when we talk about for homogeneous ones, this is what we have. So that goes. Um, all right. So for equations of that form, that's all we get. Now, if we move on to talk about the other type, so maybe we can say for equations, we already know when it's zero, it's not homogeneous, right? If it is not zero, then it is not non-homogeneous. So for equations of the form, yn plus pn minus 1, yn minus 1 plus all that plus p naught y equals q of x. And q of x is not equal to 0, right? So we can use two methods. So we have method of undetermined coefficients, okay, We have method of undetermined coefficients for simple Q of X, for simple Q of X, right? So in that case, we have you assume a particular solution, assume a particular solution, yp of X based on Q of X, okay? Then B, you then substitute into the equation, and solve for coefficient. So we already did that for order two, and solve for coefficients. Okay. So that's when we talk about method of undetermined coefficients. Then we can also have variation of parameters. There's D operator too. I already talked about D operator, but I'm not doing that here. Variation of parameters. So yeah, variation of parameters is powerful for for general Q of X, for general Q of X. So if Q of X is simple, you can use undetermined coefficient. But if things become complicated with Q of X, then you have to use variation of parameters. And what we do here basically is to solve. So you solve the homogeneous equation, solve the homogeneous equation for the fundamental solutions, or the fundamental, or what we call complementary solutions, for the fundamental solutions. So for the fundamental solutions, y1, y2, and all of that up to yn, we did variation of parameters. So you can, if you've seen the video, this is not new. Then the next thing is you now assume, so you assume that yp of x is the same, or let me just say yp for to make things simpler, but we know it is a function of x automatically. So yp is u1 y1 plus u2 y2 plus all that plus un yn. All right. So assume that. Then the next thing is C. You can now solve for all the UIs using integration. So we did that with variation of parameters. So you can refer to that video if you have not seen it. All right. So after that step, now we then go to a very important concept, which is linear independence. Linear independence that comes under variation of parameters. Linear independence and the Wronskian, linear independence and the Wronskian. So that comes up under this kind of higher order stuff. So linear independence and the Wronskian. So we say that the Wronskian, we've done that also under variation of parameters. The Wronskian is used to check. It is used to check whether solutions y1, y2 up to yn that we saw above, right, are linearly independent, whether they're linearly independent. So if they're linearly independent, that means they are unique solutions. But if they are linearly dependent, that means there's no difference between all the solutions. So one solution could then represent everything. So in that situation now, we have that the Wronskian of y1, the Wronskian of y1, comma y2 up to yn is given as the determinant of y1. What you have y1, then you differentiate that y1 prime up to the uh, n minus 1 derivative, okay? And the same goes for y2. So you have y2 prime, and then all of that down to y2 n minus 1. So you differentiate n minus 1 times, and that goes goes until we get to, until we now get to yn, and then you find yn prime, and then you also find the nth derivative of yn, okay? Yn minus 1. So you find the determinant of all that. That gives you the Wronskian. And these are the things you infer from the Wronskian. If the Wronskian is not equal to 0, okay? If the Wronskian is non-zero on some interval, so you can say the solutions are linearly independent. They are linearly independent. Okay. So you can then go further and do other things you need to do. But then if the Wronskian is equal to zero, then the solutions are linearly dependent. They are linearly dependent. That means that only one solution is good enough to represent all the rest. That's the idea there. Okay, so having taken care of this nice idea, then we can take an example. We'll take just a single example, and that can help to deal with any other example that comes. So I want to solve the trying to see. Okay, we just solve a simple homogeneous equation and leave it there. Of course, you already know the other ways to go. Okay, you already know variation of parameters, so you just use the same thing. So solve the homogeneous equation. Solve the homogeneous equation. Y prime 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 prime. That's fourth derivative minus 4y prime 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 plus 6y prime prime minus 4y prime plus y is equal to 0. That's what we're solving. And if we're doing that, you know, let me go with this now. If we are solving this, we go for step one, like we already know. Though it's higher, that it's the same idea basically. So we have the characteristic equation, the characteristic equation. Okay. So here now we are, if we assume, just like I said earlier, assume y is equal to e raised by rx, leading to r raised by 4 minus 4r cubed plus 6r squared minus 4r plus 1 equals 0. Okay. And factoring, we have, so if you factor this, you discover that it is actually r minus 1 raised by 4 equals 0. Okay. R minus 1 raised by 4 equals 0. In that case now, we can say we have a repeated root. We have a repeated root. R equals 1 with, so it's repeated 4 times with multiplicity 4. So it is repeated 4 times. Okay. So if that is the case, then we can go ahead and talk about the second step, step 2, where we write the general solution. So write the general solution, write the general solution. And of course, to write the general solution, we already have an idea. So we say for a root with multiple m, the solution, the solution includes, the solution includes powers of x, powers of x multiplied by e raised power rx. Okay. So if that is the case, it means that our y of x is simply just going to be constant c1 plus e raised power, so that'll be constant c1 e raised power x because r is 1 here, plus next you now have c2 x e raised power x, right? Then c3 plus c3x squared e raised power x, and that goes all the way since we have four multiplicities. So we have to keep multiplying by x each step because if not, the values are basically the same. So then we have c4x cubed e raised power x, okay? Because of the multiplicity. So if they were distinct, then we'd have had C1 for first one plus C2 next one plus C3 next one without needing to multiply by x. But because of the multiplicity, then we have to keep multiplying by x each step to distinguish one from the other. So here we basically have C1 plus C2x plus C3x squared plus C4x cubed all raised power e raised power x. And that is the solution to that homogeneous equation. Of course, here we say where C1, C2, C3, and C4 are arbitrary constants. So they are arbitrary constants. Okay. So the next thing you do after this is step three, where you verify. So linear, you can verify linear independence using the Wronskian. Using the Wronskian. Okay. So we can say the Wronskian determinant is W of Y1. Okay, or I can even go ahead and say W of what are the solutions now? We have e raised power x, x e raised power x, x squared e raised power x, and x cubed e raised power x. Those are the solutions. And that is simply equal to, so we now take it step by step. So you have e raised power x. If you differentiate, if you have four results, so you differentiate three times, Then next one you have x e raised power x, that becomes plenty. And then you have x plus 1 e raised power x from the law from function product rule. So you have x plus 1 e raised power x plus e raised power x. Next you have x plus 1 e raised power x plus 2e raised power x. So that's for the second solution. Next you go for x squared e raised power x, and in that case you have x squared plus 2x e raised power x. Next, you have x squared plus 2x plus 2 e raised power x. Lastly, you have x squared plus 2x plus 2 e raised power x, and then plus 2 again, x plus 1 e raised power x. And that's not the last. You still have the last one, x cubed e raised power x. Okay, so this one is x cubed plus 3x squared when you differentiate e raised power x. Then if you differentiate this one now again, you have x cubed plus 3x squared plus 6x k e raised power x. Then next you can now have x cubed plus 3x squared plus 6x plus 6, okay, plus 6, all of that into e raised power x. So that is the Wronskian determinant. Well, I mean, from all indications, the W here is not equal to 0. Okay? W is not equal to 0. You can already see that by the time you do this, I mean, it's a complicated thing to do, but we won't bother so much about it. So we can then say that since this determinant, this determinant is non-zero, since the determinant is non-zero, the solutions are linearly, the solutions are linearly independent. The solutions are linearly independent, confirming completeness. So uh it means that the solution is complete, confirming completeness. Okay, confirming completeness. So you can then conclude, you can say thus the final solution, thus the final solution is y of x equals c1 plus c2x plus c3x squared plus c4x cubed multiplied by e raised power x. So that is the solution to that fourth order problem. Okay, so on this note, we have come to the end, but before you go, we want to look at some practice. So do you want to try some out? So solve the following, solve the following higher order ordinary differential equations, right? First, you can have y prime prime, third order 6y prime prime plus 11y prime minus 6y equals 0. That's one. Two, you have y 1, 2, 3, 4, fourth order minus 5y prime, second order plus 4y equals 0. Okay, how about number 3? You have y 1, 2, 3 minus 3y 1, 2 plus 3y prime minus y equals x e raised power x. Okay. Okay. I'm looking for, okay, in 4 now, determine, okay, let me just use a general rule and then I list them as 4, 5, 6. So determine whether the whether the given functions are linearly are linearly independent, that they are linearly independent by computing the Wronskian, by computing the Wronskian. Okay. So I can list that as 4 now. So 4, you have for 4 now, you have y1 equals e raised power x, y2 equals e raised power 2x. So you want to compute the Wronskian. So like what you need the Wronskian y1, y2 for this. Okay. Number 5, you have y1 equals x, y2 equals x squared, and y3 equals x cubed. Okay. Number 6, you have y1 equals cos x, y1 equals cos x, then y2 equals sine x. Okay, you have that. And then you now have the last one. Okay, I can squeeze that in here. Okay, or let me just put it separately. Question 7, say solve y 1, 2, 3, 4, fourth order minus 2y prime prime plus y equals 0. So those are some things to practice. So let me see your answers in the comment section. Let me also see in the comment section how helpful these videos are for you. And if you have a topic you'd like me to teach or a problem you'd like me to solve, then if you have subscribed, thank you so much. If you haven't subscribed, please go ahead and subscribe right now. And for everybody, please don't forget to hit the notification bell so you can always get alerted each time a new video is released. Also, like and share these videos so that more people can have access to this vital teachings. Till I come your way again, keep doing maths right. Bye.